I'm wondering how that works at night. All right, is the audio working okay? Okay, cool. I have a little feedback. But anyway, so yeah, thanks so much you all for having me here. It's been 6 years since I've been to Brisbane. I actually lived in Australia for about 4 years. When I first left Brazil, where I'm originally from, that's one of the reasons my accent is a mess. So actually, if you can't understand something I say, just ask later or just raise your hand or something. I tend to kind of say words using different accents depending on when I learned them. I've learned a lot of words in Australia, so maybe some of them will be familiar, or the accent will be familiar, but you know, it can get funny. Anyway, so like I said, I work for a company called Buoyant. We are super tiny, 20 people, developers, really. We might have 1 or 2 other non-developers. The company is based in San Francisco, but I live in New York, so I work remote, which is a whole different topic that I would love to have a talk about some other day. But I'm here to talk about, as I said, let me just back to the title, the next gen of microservices, which is a super catchy title because, you know, next gen microservices, same word. Who here has heard the word microservice as spoken by a speaker in a talk today? What about Docker? What about Kubernetes? Interesting. In Melbourne, there was definitely more Kubernetes than Docker. And we used to joke that every talk must drop the word Docker here or there. It doesn't matter. It could be talking about JavaScript. You must say Docker. Now Kubernetes seems to be the thing to talk about. We're going to talk about all of those things, so don't worry, because we will cover them. Anyway, as I said, I work for Buoyant, and Buoyant is a software vendor. So we produce some stuff that's open source. You offer support if you want. But something I've learned is that having migrated recently from consumer tech, where I was working for, you know, websites that you might use when you're having fun, listening to music, watching videos, whatever, to the infrastructure space, I'm extremely conscious not make this a sales pitch. I'll try my best not to mention any products, my company or otherwise, and just talk about ideas. But I know that it's going to be a little bit complicated because one of the reasons I joined Buoyant is because we are working on this space. We're actually producing infrastructure that works well for microservices and kind of drive people to the next stage, hopefully. So there's a little overlap, hopefully not too much. Hopefully it's not going to feel like, you know, I'm trying to push you anything, because I'm not. If you want to talk about anything by Buoyant, I can talk about later. I'll be here for the whole day and tomorrow. More than happy to, I know, let you talk to our salespeople, because I don't really sell anything. But also technology and LinkedIn and things like that. We're going to also, the one thing I will say is that we're going to make a big announcement at KubeCon next week. So stay tuned for that. But OK, this out. This is not a sales pitch kind of slide out. Let's talk about microservices, right? And the first thing I find, having been giving talks on microservices for a little, I don't know, maybe a few years, whatever, now, is that we need to create some kind of common definition we can work during this talk. We work in an industry, everything is really ill-defined, and you know, different people talk about the same words in different ways. So just for the sake of this talk, I want to focus on some aspects of what I believe constitute microservices. And you might disagree, you might agree, I don't know. But for this talk, it's going to be much better if I actually share some words in common. So the way I want to think about microservices for this talk is highly distributed application architecture. And why is this important? Historically, we've built a lot of applications as big pieces of software. You might call them monoliths if you really want to talk shit about them. But otherwise, it's just the way things are. But interesting enough, that hasn't been the case for every single piece of software we've built. We built distributed file systems, distributed databases, distributed everything. It's just that we haven't so far spent a lot of time on the application layer trying to distribute things. Maybe if you go like late 90s, you talk about Corb and things like this. But I don't think that would apply to as many companies proportionally as we're seeing right now, organizations or projects or whatever you want. Anyway, so we're talking about, again, just as a working definition here so we can move forward. You can think of microservices as highly distributed application architecture. We're not going to talk about sizes. We're not going to talk about how many, whatever else. This is off. We're going to talk about distributed architecture. And something interesting is that highly distributed application architecture can be seen as just a flavor of just distributed computing, which is something that's been on since forever, right? If you this Andy Tannenbaum has some very interesting work from probably late 80s, early 90s on distributed operating systems that I read a lot about back in the day. And it's kind of the same principle, but just applied to your application layer. So that's okay. Like, if you assume that these things are correct, at least, again, for this talk, we have a case of distributed computing here. And ultimately, what I've seen over and over working on the application layer or even the infrastructure layer is that distributing things cause some interesting problems. And I just realized I'm not allowed to call them problems. They are challenges. So we have a lot of challenges. Some of them on the organization side. How do we structure organizations, teams, processes to work with all this distribution? But others on the technical side, right? What are the actual implications on the software end? I have spent a lot of time talking about the organization side. I've built on work by Martin Fowler, James Lewis, and others, and on a lot of the experience I've had at SoundCloud, in which we built a 300 engineers organization working, I don't even know how many microservices, and actually was very good for the company going down that path. But we had to change a lot of things. There are many things that we've learned throughout this stage. So I don't want to talk about that anymore for this particular presentation here. We can talk again. I'll be here. Let's get a beer and talk about that. But I want to talk about the technical problems. And because I kind of abstract microservices so much, I don't even need to create something new to talk about the technical problems. I can use something that's super old, which is Peter Deutsch's 8 Fallacies of Distributed Computing. It's if you're not familiar with this work, there's enough material here to cover many books and many talks and a lot of things. So I don't want to spend a lot of time in it. But I definitely invite you all to familiarize yourself with that. It was a list created by Peter Deutsch and other people, including James Gosling, who's the Java architect. And it pretty much, you can think of it as what breaks when you distribute a system in terms of technical aspects of what you're building. It's like really a come to Jesus moment where, you know, all the assumptions you might have will break. And it's also known as 8 ways in which everything goes to shit. So again, if I don't want to go item by item, we don't have a lot of time today, but if you just kind of glance over it, you're going to feel that maybe there's a pattern around not relying on things to just be there. Not just making a call and expecting that the server is going to respond. Not expecting a call to be to take no time. Because, you know, you might be used, everything's running on the same VM, process, whatever, and invoke a method, it's back before I even think about it. A networked or distributed system might not be like this. So this is an interesting list of requirements that we need to address when building distributed systems. It was really contained when we were only building infrastructure systems, but now we're going up the stack, hitting the application, and applications need to start thinking about it. Now, again, limited time. There are so many different things we can explore around these 8 items, but I want to focus on one particular example, something that I'm sure you all have had if you had any form of distributed system application or otherwise, which is how do we recover from temporary failure? And temporary is we could say many different ways. But what I mean by temporary failure here is that service A or system A calls system B happens to be not able to respond right now. Maybe because somebody's deploying some new code and it's still like rebooting or whatever. Maybe it's because it's actually down. Maybe because the network's down. Maybe there's a bug. I don't know. Something's going on. But the most interesting qualifier here is that actually in some time, this system will be able to recover. Maybe the deployment has finished and it's back up. I don't know. Something like this. This happens all the time when you have a highly distributed architecture. And it's something one needs to deal with. So because we're talking about next generation or current generation, let's talk about 2013 and the way I perceived things were at back then. At 2013, I was at SoundCloud for probably 2 years. We started as a big monolithic Rails app. We started pulling things to microservices. We actually started working for us after a lot of blood, sweat, and tears. But if you came to a conference like this, I tried to get things from 3 interesting conferences. Or my favorite conferences. You might have been here at YOW 2013. Maybe you went to one of the GOTO conferences they have in Europe and North America, and QCon's kind of 3 famous ones. You're going to see a lot of experience reports from different people. I think in this sample, I don't expect you to read any of this. It's just really, I'm on the visual side. There are things from Google reporting how they did things, LinkedIn, and that's what There's Zynga here. It doesn't get more 2013 than Zynga, right? Farmville and all that kind of stuff. People annoying you on Facebook, yeah. So yeah, how these people were dealing with this problem. You would come to a conference like this, somebody would say, oh, that's how we're doing. We've written this kind of software, that kind of software. We have these and these and these patterns implemented. And because we are who we are, we go back home and say, I know, that problem I have at work, it doesn't really matter what the problem is. I'm going to use microservices. That's it. It's the way to go. And let's be honest, 2013, you're not going to start with microservices because you already have something. Otherwise, you wouldn't have a job to begin with. So you probably like, OK, that new module or this particular piece of code that's just being a pain to deal with, I'm going to extract it to microservices or do something with microservices. As long as you use the word microservices, you're cool. So you do that, and you sit down, you write a little bit of code. It's probably going to be a few hundred lines, tops, and it's beautiful because it's just business logic. It's all you can see. There's no plumbing. There's no, boilerplate. There's nothing like this. And because you're probably, if you're doing microservices like this in 2013, you're probably a hipster. You're probably also using a different programming language. I would bet you're using Go, because that's what cool kids were doing back then. And then you go to Medium. I actually don't know if Medium was up in 2013, but some Medium equivalent, medium.com, and you would write a blog post about how Go was the best, so much better than Rails or Java or whatever, because you're just writing 200 lines, and it's amazing, and oh my God, it's so good. Everything else is shit. That's us. So that's interesting, except that over and over again, I've seen this, where people would start extracting a service. At SoundCloud, our first service was the payments system, which used to process a few $1 million a month, and it was built in the Rails code base. We extracted it out, and we would then, it was good. It's good, ready to go to production. And then realized that we had to wire it back to something, right? Because a microservice in isolation doesn't really get touched by anybody. We've done what a lot of people do, which is we had the Rails monolith. We just made the Rails monolith talk to the inner service. It's awful, but it's a good first step. It gets you to get your service out on the internet. Eventually, we evolved to something called a BFF, which is a pattern that we've talked a lot about. But that's how it started. That's cool. But the problem is that your little code base now has some layer on it. You have to deal with RPC. You start needing to worry about a lot of weird conditions. You might, 2013, you're probably using JSON and HTTP1. So probably, you at some point, maybe you came to YOW, maybe Jim Weber was here, you got drunk with him, he convinced you the rest is the way to go. So you're thinking about status codes and hypermedia and whatever else it was. Don't really remember, got too drunk that night. So there's some logic that you have to deal with. OK, cool. But back to our example, something that will absolutely happen is that your service or the service you're calling from whatever service you're building, it's going to have problems. Every now and then, it's going to be down. It's going to recover, but it's going to be down. So that's complicated. It's like, oh my God, what do I do now? We start having catastrophic failures and not knowing what's going on. Super fun. And because you kind of this hipster developer, you've been to conferences like this, you know what's in, you've read the books, and you're probably familiarized with the work by Michael Nygaard, who I believe actually was here in 2013 in Brisbane. I'm not sure about this, but I think he was. And you might have been to workshops and read his book. If you haven't read this book, just do it. This is actually the second edition that I think comes up next month. I haven't read the second edition yet, but the first one is just a classic in our field. And Michael's work is very much something around stop pretending that all this is going to work. Just learn how to deal, put on your big boy pants and learn how to deal with failure. That's all it is about. So there are many interesting patterns in this book, and one of them that I think applies very well to the situation we're talking about right now is something called a circuit breaker. I'm not going to go into super detailed explanation of how this works, but you can think of a circuit breaker as something in which your client makes a call to a server, the server is on fire, doesn't respond or responds something that's garbage. Instead of making another request, you wait. Why do you wait? Because the server might be bootstrapping. Maybe it's actually just having some temporary failure, some memory somewhere it's not working well. So instead of hammering the service more and more requests, retries all the time, you actually just chill. It's the same principle as a circuit breaker in your house when there's some electrical thing. It just flips. I don't know a lot about electricity. Anyway, and eventually, hopefully, we'll get back to normal. So you wait a little bit, and you try again, and maybe actually it's still broken, but hopefully not as much. And then you wait again. And there are some interesting things about how much you should wait, when you should stop waiting altogether, and maybe just, I know, one pager duty or whatever Nagios thing you might have. There are various interesting things around this. But the point is that you wait until the service is bad, until the service is kind of back to normal, instead of just hammering with all this kind of stuff. So somebody will read this book in your team, and they're going to say, I know, let's implement circuit breakers and timeouts. And you do, and you end up with more stuff in your code. And I would also add, I kind of merge them together, but I hope it's okay, telemetry data as well. Because if you start having these problems, I know in 2013 we had absolutely no culture of observability outside of the big companies. I've suffered with this so much. And then we started using the stats. I think Etsy was kind of the biggest driver around this because they published a statsd. And then realized that statsd uses a lot of disk space, so we start getting alerted for the alerted system. Then we, no. Anyway, but that's something that kind of came together. It's cool, but something to keep in mind is that microservice architectures are highly distributed, blah, 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 but there's something that makes them a bit more different and harder to deal with, which is you have a shitload of services. So you don't have just many instances of the same client. You have many instances of many different clients. Maybe your public API is hitting your service, your web UI is hitting your service, your internal tools is hitting your service, and because 2013, your VCs are like mobile first, so you start having to have mobile APIs as well. And all this stuff is just hammering your service over and over, which transforms this very simple model where you have one client, one server, blip, 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 to something crazy, where maybe the first client asked for the message, and then you decided to wait because the message wasn't good or whatever it was, but then a second client came in just then, because he didn't know about the first one, right? And it's like, oh, okay, I'm going to wait. And while these two are waiting, somebody else comes, and somebody else comes, and somebody else comes. And that, instead of going from big flame to small flame to happy face, it goes from big flame to small flame to big flame again, blah, 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 until you hit what I just found out this week's 2016's Word of the Year, dumpster fire. And I'm very sure I have contributed to that. Anyway, it's a big problem, and it's very hard to manage. But because of the way our brains are wired and we like order, we don't like chaotic stuff, somebody would look at that, like, I know. Let's just have all circuit breakers share state. Now, this is a shortcut because nobody would ever say share state because they know that's bad. They would say, let's coordinate our circuit breakers. Let's have a federation of circuit breakers or some shit like this. But what it means is that they will share state. So they do that. And this sentence, I need you to remember this one because this is very useful because it's also the answer to the question, how the hell did you end up relying or depending on Zookeeper to begin with? There's only 3 reasons for anybody to use Zookeeper at this stage. If you've worked at Twitter before and you really miss being in pain, because Twitter uses Zookeeper for service discovery to this day. If you've done this, or something similar to this, or if you use Kafka. And I think the latter is probably going away or already gone away. It's been a while since I used managed Kafka, or unmanaged Kafka, but it's very painful. Anyway, we end up with that, and obviously your code stack just keeps going. But now there's an interesting challenge right now, which is, I'm going to flick through the slide super quick because out of order I just realized. Which instance should my service talk to? You know, you have lots of different services. It's an instance of the same service. Some of them are just dead, some of them are bad, some of them are doing well, you know, all this kind of stuff. But how do you know? How do you know which one to talk to? You have a list of IPs or host names or whatever, and you need to know which one to talk to. Well, in 2013, you're probably using DNS. If you're super lucky, you're using SRV records. Who here has used or used SRV records or DNS? So if you don't know what that means, it pretty much is the same stuff as DNS, except it comes with the port as well. So instead of just getting the IP, when you ask for a service, you get IP port. That's actually very useful because you don't need to have a lot of conventions around which port to use. Like, oh, our services use port 80 or whatever it is. You can actually have them be configured. But DNS doesn't know about the state of any of this stuff. DNS is like, dude, they just work here. See, whatever, here's a list, just do your thing. And then you end up in a situation where, now I'm going to go back, please. Yes. Which is, I know, let's just have the client know which instances are healthy, which are not healthy, and kind of manage that. Now, this is something that at SoundCloud we stole straight from Twitter. Just like I was talking to some person from there at some conference, and they mentioned this, like, oh my God, we need this like yesterday. I wish we had done, we probably did this only 2014 or 15, but I wish we had done this way back. Because it actually, if you're finding trouble with this kind of thing I'm talking about right now, just think about this, and maybe let's talk later, because this can save lives. Seriously, it's amazing. And what it means is that your client knows, well, you receive a list from DNS or whatever you use, and you know which servers you've talked to, which one are okay, which one are responding badly, which are slow, which are fast. Maybe you can guess a lot of different things. And there are many interesting algorithms you can use to prioritize which service you should talk to, make sure you're not overloading others. This is amazing, but it's also a lot of code that you need to write. So off you go. You have now your interesting stack of stuff that you need just to get one RPC call in your beautiful microservice architecture. Meanwhile, the user is still waiting for that, I don't know, logout button that you promised them ages ago. But to make it more interesting, you want to think that this is just for RPC reliability that we're talking about here. Now, there are so many other things that one needs to do when it comes to distributed architecture. We're not talking about security, performance, even observability largely. We're not talking about any of this. It's just one particular slice that we are trying kind of shaving off here. And so, but then brings the question, okay, what makes 2017 different? What's on now that wasn't there? And 2017 is almost over anyway, so it's a weird one, but whatever. What makes today different? 2017 plus minus 2, maybe. I would say that the way I perceive it, a lot of what we had as experience reports back then became actual software released by different companies. First, I think this is just normal. If you look at things like Hadoop and various other projects, Cassandra, DynamoDB, this is just how it happens. Somebody publishes a paper or gives a talk, and then the community implements that. But something that's different this time around is that it's not only the community implementing it. It was also a lot of people who have left the big companies and created their own little infrastructure companies, trying to sell support. Oftentimes doesn't work very well, but they publish a lot of open source software as their business. And that has changed the landscape a lot. I guess one interesting example here might be that I know firsthand is Prometheus, which we built at SoundCloud as a way to, well, we built it because we hired too many people from Google, and they were really unhappy with StatsD. But now, most people, if not everybody who was originally part of this project back then, is actually supporting this system as their main job. And that's very interesting, and a lot of this happens. So a lot of these things, if not all of them, came from big companies, and it's just examples of things I particularly know. So the way it works then is that instead of having to write all that code yourself, instead of going all the way down the stack, or writing every single component of this stack, you can actually rely on these things, which means that oftentimes you shave them to the side and use them as libraries. At SoundCloud in particular, we used a lot of the Finagle library. At DigitalOcean, when I was after, we were using a lot of something called GoKit, which is actually, funny enough, built on by somebody who used to work at SoundCloud, but it works for Go. We were doing importing this library and making our service resilient by using these libraries. And in our case, SoundCloud was maybe 100 developer, if 200 million users probably at this stage. And we were able to use the Finagle stack, which was built by Twitter as open source software, and had things in there that we just did not understand. We look at it as like, holy shit, who would ever use this? Client-side load balancing was one example of this. I don't understand why anybody would use that. But then we would acquire 10 million users more. It's like, oh, wow, that's why we need it, because everything else is on fire. So that's kind of how it works. And that can work okay, but I would say, as somebody who had to manage a situation like this for close to 4 years, it's not my preferred way of working. Because, again, you're adding a library to everybody's services. The first problem you have is that all services need to be in the same language, right? SoundCloud, we were lucky enough that we kind of standardized on JVM. At DigitalOcean, whereas after, we standardized on Go. But still, every time there's a new release or you find a vulnerability or whatever, you need everybody to deploy new versions of the library, stop what they're doing. It's a nightmare. I cannot tell you how many angry emails I had to send to people, say, please upgrade all this stuff now. It never works. Nobody reads email, apparently. I should have Slacked them or something. So it's bad. And something I've seen is that people think that this model is more manageable if you use a monorepo, which pretty much means that instead of having multiple different repositories on Git for your multiple different services. You just concentrate in one big repository. In my experience, it doesn't help at all because, sure, maybe you make a change to a library and you're able to change all systems that depend on that library, but I'm yet to see a company that deploys all the services at the same time. So if you do that, what you end up with is a system, it's a kind of an ecosystem in which the head of your version control system, Git, doesn't actually match what's deployed. It's going to take a week or something to converge, and by the time it converges, it has already changed again. So we use a monorepo right now at Buoyant. I've used one at DigitalOcean. I still am very much not in favor of this approach. It's something that I worked a lot of Twitter people. Twitter used it. They like it. But I kind of don't see the point, to be honest. Anyway, so we had this library. There are problems. There are ways around it, but there are problems. But there's something that might be an interesting, different way to think about it. So we're talking about having all this code that actually doesn't really do much that's specific to your business, right? It's just like bytes in and out, and if these bytes are flagging as error, you break these, and there's nothing about whatever your domain model is. Oh, it's also an interesting rule of thumb that I would apply to any library. Things become much more manageable if you don't let any business logic leak into your library. So if you actually go down this path, just make sure there's no business logic inside these things. Anyway, some things I was going to leak in, but try your best. Anyway, back to where we're at. We have this library that does a lot of interesting things, but nothing that's in there is actually related to your application. It's just commodity stuff. And big companies like, I know, Google's and Facebook's can afford having people working on that, but not everybody can do that. So if you kind of start exercising this kind of thinking process, you may want to think about it as kind of a layer that sits on top of a network. Now, before anybody throws a copy of TCP Illustrated here on me, I will fully acknowledge that this is kind of hacking or bastardizing the TCP IP stack and OCI, whatever else. All these things actually belong to the application layer in TCP IP. I'll just claim that, sure, it's correct, but it's not very useful for this discussion. What we would be interesting to have some kind of that goes on top of the TCP IP layer, on top of what we have now, that actually is more aware of the modern, next-gen, whatever you want to call it, needs that we have for services. And that's interesting. I was thinking a lot about that. And then comes the question, like, so how does one go about adding a new stack, a new frame to your, a new layer, I guess, to your TCP IP stack? Is that a repository I can send a pull request to? It turns out it hasn't. The IETF has a GitHub organization, but they don't do much there. But that's an interesting problem. Okay, we're talking about building a fundamental layer on your network. How is that even possible? Now, there's one way we can hack around these things, which is using the concept of sidecars. But first let me explain what sidecar is. If you think about the dotted container as your application, your service, and we were just saying that the grayed out area is kind of a library you're using, and then you think about the scary outside world where everything goes to shit, or it's the kind of brown box, good color. So the back and forth between them is just direct, right? The application opens a socket, talks to the service, back and forth, and the application needs to deal with all this stuff. Now, there's a different approach, which is adding something in the middle. So instead of your application directly talking to the outside world, it goes through what's effectively a proxy, but in this model, we deploy in something we call a sidecar. I'll give you an example of the first time I saw this. At SoundCloud, again, we had this big monolith, which was a Rails code base, and we're building all this new cool stuff, hundreds of services, they're all using all this kind of fancy, nice technology. But every time they talked to the monolith, they would have to be extra careful because the monolith was very fragile. It wasn't meant to do any of this. I have no idea what they're doing now, but SoundCloud was still running Rails 2 until I left in 2015. So probably, I don't know, 5 versions behind. It was very hard to maintain, very hard to do anything, to change it. And change it was a mess. Nobody wanted to touch that code base. So instead of investing a lot of time, actually we tried investing a lot of time in modernizing it and failed 3 times. But at some point, like, you know what? For example, we needed all of our other services were migrated to Thrift from HTTP and JSON. Instead of trying to make Rails speak Thrift, which is very hard, we just built something in the middle, that was a small JVM app deployed on the same host as all Rails processes that would actually do the translation between the thrift inbound and the HTTP JSON outbound. So the monolith didn't have to know anything about thrift or whatever was going on. The translation was done at the JVM layer. And because it was a JVM app, we could actually use the same libs we're using everywhere else. This is how we started doing it there. Airbnb was probably the biggest case of pushing for this approach for service discovery. They have something I think called the Smart Stack that they released in 2014 or whereabouts, where they did something similar. And Netflix has a lot of these as well, because at SoundCloud we're able to keep everything using the JVM as much as possible. Netflix had this problem where, if you know anybody from Netflix from back around this period, they would come to presentations like this and talk about all this fancy stuff. They'll talk about the Java stack. They also had the Python stack on the side. And the Python stack needs to be compatible with all this stuff. So they created more and more of this sidecar approach to enable the Python systems to enjoy the benefits that the JVM systems were enjoying. I have no idea how it's going now because I have even more languages, but that's the reality. So we have this interesting sidecar thing that's a proxy that sits between the real world and your application, and it's deployed with your application, right? So in the Rails case, we would deploy, I don't know, let's say 10 processes per host, and on top of them, or together with them, one of these JVM processes where everything goes through, and inbound and outbound connection come through this proxy. On more modern approaches, you might want to deploy one process. Either if you're using something like Docker Compose, you could deploy as one independent container that is deployed within your Docker Compose file, or you could actually have a different model where it's a process within your container. Not really the best way to do that, but it's possible. Anyway, interesting thing is that you have sidecars controlling inbound and outbound traffic, which means that effectively you have sidecars talking to sidecars with something like this. Something that people who have been pioneering this approach have found is that it's actually very hard to get to this state because a lot of the ways to make traffic go through the proxy is through configuring the proxy settings, HTTP proxy settings or whatever else you're using. If you ever try to configure proxy settings on the JVM, you know what I'm talking about. The two things that the JVM does horribly is proxy and DNS. For DNS, you have libraries. For proxy, we all know. So it was very hard for people to configure that, but then something has also changed in recent years in which platforms like Kubernetes, which I'm the most familiar with, but I'm sure others do the same, allow for you to change network rules and network routing underneath where the application is. So effectively, what you're doing really is like writing IP table scripts. I spent 2 weeks this year just writing IP tables, but it's great because you can redirect traffic in whichever way you want, which allows for us to create this interesting kind of virtual or overlay network on top of the real network where proxies are talking to proxies. And that kind of enables us to go for some of the interesting solutions to the problems we were discussing. Because a lot of people were doing this, some as products, some just as internal implementations, people eventually named it as a pattern because that's what we do, right? We like creating patterns so we can write books, create companies, go to conferences, give talks like this one. So my boss, William Morgan, actually was the person who came up with the name Service Mesh a while back to describe what we were working on. There are various different implementations. My company has some, many other companies have. There are open source implementations and like closed source add-on for Nginx and HTTP and things like this. But that's what we usually call this approach, as Service Mesh, and it's trying to solve some of these problems. That's interesting, but how does that impact your service for real? Like what actually changes? You can think of it as, remember the stack we had? It's where things were going up. Visualizing it a little bit, you could think that these things are being pushed down. So they actually become part of the platform. Your service can be a little bit of the business logic. And I mean, I won't be able to come here with a straight face and it's going to be just business logic. That's bullshit. It's going to be some RPC, some all the kind of stuff. But a lot of the heavy lifting and a lot of the dumb stuff can be pushed down the platform. And that's what we've been seeing more and more with this approach, where everything that we've been talking about so far can actually be pushed down and become part of that network. The way it works is that the same way you don't have to worry about when you we want to read the contents of a file, you just say, hey, file system, I want /etc/blah, blah, blah, and you know it's going to be returned if it exists. It's the same, you can go about all these other things right now. It became part of the platform. You don't really need to know a lot about how it's implemented internally, or your application doesn't. And if you think about like all these kind of things I had mentioned before, they're pretty much under this box of stability. So something interesting about the work here is that as we said in the very beginning of this presentation, this is just one example that we're going to use. There are other things. In fact, if we just go back to the work we were using to create this first example, Michael Nygaard's work, he has, and this is from the second edition now, so it's going to get a bit confusing, but he has, I don't know, maybe 5 different kind of coarse-grained areas that would have to think about when having a distributed system like this one. And that's just one pattern catalog. You probably have other things there other people have discussed and worked on that's not covered by this book. So the fun thing is that you can, for most of these things, you can actually apply the same approach and push them down the network. Again, your application is not going to be the beautiful 100 lines of code that does nothing but business logic. There's going to be some stuff in there, but it's going to be much less than what it was when we were first doing this in 2013, plus minus 2 years. And the combination of all these things, all these different concerns, it's what we're calling a service mesh here. It's this fundamental component that runs just between your actual network and your application that allows for you to do all these kind of interesting things. One way to think about it is going back to the fallacies of distributed computing is that it allows for you to kind of pretend that some of these things are actually not fallacies, they are true. Oh, I mean pretend because they are still fallacies. You're just delegating the work, you're outsourcing it to a layer. And I also understand how confusing this slide is, because now you're wondering if the ones that are true are the ones that are still there, or the ones that are ticked off. I know, I figured that out, that this was going to be very confusing just before coming here. But no, I mean, the ones that I think you can kind of start pretending are not true are the ones that you can still see. The network's reliable, the network's secure, topology doesn't change. The network's not reliable. Things will break all the time. But the kind of the smart network, the mesh can deal with that for you. The network's secure. One of the biggest things about service meshes that we see people using over and over is for mutual TLS. If you ever had to implement mutual TLS so that all of your intra-VPN communication goes through HTTPS or just plain TLS, you know how hard it is. You need to get certificates, and you need to get a CA, blah, 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 blah. Service Mesh can do a lot of this work for you for free. And the topology doesn't change. That's bullshit. The topology will change all the time. The thing is that because you're relying your service, because you're delegating your service discovery to the network understands that this container came down, this container came up, and it can redirect you to the right point. So again, you're just pretending, or your application, your service can just pretend these things are not, or are true, actually are not fallacies. They're still fundamentally broken, but that's why we're doing software, right? We just add a new layer and hope for the best. And so, in summary, before I run out of time, what I want you to think about is that it's not that these patterns aren't used anymore, it's not that they're not useful anymore, it's more like we're able to push them down the stack. We're able to make it such that our communications get them, or most communications maybe get them for free. Again, there's no such thing as for free, but there's a lot of things that you don't have to do. You can, again, delegate to the underlying infrastructure. Now, I want to talk about 3 of the main risks, if you will, or bad things that could happen if you adopt this, that I've seen firsthand. One of them is that this works much better for metadata-rich protocols. I was very conflicted on how to call this, but what I mean is things like JSON, or what else would be a good example? YAML, maybe XML, if you will, in which you can think of it as anything that's a key values protocol, where I know that name, Phil, city, Brisbane, as opposed to some of the newer protocols, which are amazing, like protobuf and gRPC on top of it, that really optimize data so much that they actually don't carry the schema with it. So if you have a metadata rich protocol, like again, just something that pushes JSON around, your proxy can read that and can do interesting things with that. If you're using gRPC and several other things, to the proxy just bites in and out. It's very hard to the proxy to detect different types of errors. Because gRPC is standardized, we can detect errors, but not all of them. It's not that easy to be smart. But again, I actually do think that gRPC is probably the best technology right now in terms of RPC. If you're using things like Go, Java, or any JVM language, I would definitely recommend you use that. If you're using Ruby, I would not recommend you using that because the generators are very problematic. But you need to know that it's an interesting problem that we might be able to solve in the future. The second one is that it kind of couples your application to the platform because of the assumptions, right? It's similar to, I don't know, back in the day when we're developing on Windows and deploying on Linux. It feels different. There's only so many things that you can rely on that your operating system is going to provide. Some services are not going to be available. All that said, all modern service mesh implementations that I'm aware of have a super small overhead. So if you want to deploy them in your machine as you're developing your code, it's actually very easy. But just be aware, it's not something that comes for free. And let's be honest, it's a leaky abstraction. It's not network. It's not part of the TCP IP stack. Things are not going to be in the mesh. Maybe your database is not going to be in the mesh. Maybe it will, depends. If you want to talk to some other service from a partner or something that's not in your network, you're not. You know, the most common thing is not even when you need to go out of your organization or because you're using a different protocol to talk to a database, is when you're on team A and you need something from team B, but team B hates you. So they're like, whatever technology you pick, they're not going to use it anyway. So, you know, the internal defensive programming, we all know that. That happens, and it happens a lot. So it's something to keep in mind. We've seen, at Buoyant in particular, we have some very large clients. And the way I see it growing is that one team adopts it, and then it starts kind of embracing more and more services, and then they realize that somebody else here has also adopted, or adopted something else, and then they have a fight. Anyway, so yeah, just keep that in mind. It's kind of a limitation on the model. So we're almost out of time. It was a lot to cover, but I hope I gave you a lot of pointers and things you can look at. Again, I'm more than happy to talk about any of these topics or anything else you want to talk about. But maybe let's have some Q&A.